Hey everyone, thanks for joining the last talk before keynote. I am Tejas Shah, and this is my colleague Rishav Sagar. We both are software engineers in AWS OpenSearch. I'm focused more on vector search, and he is in core indexing. Now, today we are going to talk about a super awesome topic of context-aware segments in OpenSearch. It's a way to store related data together in OpenSearch to get better query performance. So yeah, this is just a brief of what we are going to talk about. We'll start off with the problems with random data distribution in OpenSearch. We'll introduce what context-aware segments are, go through the benefits of it, and then give a little bit of detail on how indexing and search is going to work for context-aware segments. After that, we'll also highlight some of the features that we are planning for future, and then it will be open for questions. So let's dive into it. As most of you know, the current architecture is like, in OpenSearch is like data is divided into shards, and then it's further divided into segments. Each shard is like a Lucene index. Now, when you ingest data into the OpenSearch index, most of the times there is no way to control where the data is stored. So it's more or less a random distribution, and because it is scatter-gather approach where a query is fired and all shards gets that query, executes it, and coordinator aggregates the data, it works just fine. For most cases, it just works fine. So, but there are certain cases wherein if there is relation between the data, it's much better to store that data together so that we can leverage some optimizations. So the slide basically highlights the issues with random data distribution. So one of them is data fragmentation. As I said, like, since it's a random distribution, any document can just land in any segment, and every time we need to make sure that we go through all the segments before we can return the search results. Since data is related, there is context blindness within the shard where, if there is data relationship, it still is distributed across segments, and we cannot leverage that data relationships to optimize our queries. And as a side effect, we again have performance impact where we are just leaving gains on the table when we can't leverage those data relationships. So I have an image here in the slide where it kind of shows like how data is distributed. It's like jigsaws in buckets, and each bucket you can think of it as like a segment, and the color of the jigsaws shows the relationship between the documents. So in the current architecture, it just basically just randomly distributes these documents across these buckets. So yeah. Before jumping into like what we are doing for to not have random data distribution, I just wanted to highlight some of the very common use cases that we see with users for wherein data distribution can random data distribution can cause issues. So one of the very common use cases that we see is vector search with metadata filtering. So generally, when users store vectors inside of OpenSearch cluster, they also store some metadata around it. And oftentimes, they want to just filter that metadata before even doing like a nearest neighbor search. Now, to give some background on vector search, vector search is basically, it executes k nearest neighbor searches. Now, because brute force k nearest neighbor searches are expensive, it uses something called as a hierarchical navigable small world graphs. It's basically a layered graphs which helps do an approximate nearest neighbor search. Now, let's take an example of an index where there is an entire company data. Generally, this company data is often, we have seen, divided into teams. And most of the time, the query patterns are in the format where you only want to query certain team data, and there is no need to query any other team data. So in these scenarios, when you actually index vectors, all the team's data is created in, say, a single graph. If you just imagine a single segment, so graphs translate to segment in OpenSearch. Now, this causes two issues. Since you can also see the image where, you know, I've colored related data, like you can think of it as a team data. For each color, it represents a different team. Now, in this scenario, like there is an impact when there is data skew. So some team can have more data, some teams can have less data. Now, because of this, if there is a query which is querying for a team which has smaller data or a sparse data, there is an impact on search relevance here. So, yeah, and that's where for certain query, even though overall search relevance is good and the recall is intact, when you have certain queries related to sparse data, the recall just drops. Another issue that we see is like these vector search especially is very memory hungry. So these graphs need to be loaded inside the memory before we can actually execute search. So what happens is like there is irrelevant data that is being loaded sometimes. So there is a good chance, say, that if there are multiple segments, that means there are multiple graphs, and there is a query, and one of the query just won't return sometimes any result because there's no relevant data inside of it. So we still have to load that graph, go through, execute the search on those vectors, and at the end we don't get any results from that particular segment. So there is a resource wastage in terms of CPU utilization, and it also adds up to the latencies. Another common use case where data grouping, like random distribution, can be a minor issue is like a log analytics use case where you know, you want to query anomalies like error logs more than the success logs, but error logs are generally very sparse. And still we have to go through all the segments in the current architecture. So the main impact here is like queries are slower, and there's no issues with data skew in this particular use case, but it's just that they're slow. So now this sets the stage for the introduction of context-aware segments. I'll let Rishav explain you what those are. So yeah.
Thanks, Tejas. As it was highlighted by my colleague, OpenSearch currently lacks a native way to support group related data in the same segment. This essentially causes both search as well as compute wastage, regression in the search performance as well as the compute wastage. So in order to fill this gap, we introduce something called context-aware segment within OpenSearch, where OpenSearch will strategically co-locate related data into the same segment or a group of segments. The idea behind co-locating data here is that to align the segment boundaries within a particular shard with the anticipated query pattern that we expect on this particular index. So this essentially, by grouping the data together, related data together, we ensures that documents that are frequently queried together always resides in the same set of segments. Now, to visualize this further, going back to the previous example of jigsaw puzzle, like which my colleague shared earlier, where puzzles were randomly distributed across the segment buckets. Like with context-aware segment, what happened was, since we are storing related data, related pieces into the same bucket, this streamlined even document retrieval part. So as we can see, like the colors, the puzzles that having the same colors belongs to the same bucket. This essentially improves the overall search query performance as well. Beside this, there is couple of more use cases that we discussed earlier. One being the vector search, where earlier with the current implementation, the relevant data was distributed across a different HNSW graph. Now, with context-aware segment, vector search will now create separate HNSW graph for different groups. This again helps in the overall query performance, as we will be iterating through only the documents that are relevant for this particular query. Also, this improves the overall compute resource utilization, since we don't need to load the entire HNSW graph, and we will only load the HNSW graph which is relevant and the document and where the documents will be present. Similarly, for log analytics, by applying context-aware based grouping, context-aware grouping based on the status code, we ensure that anomalies, which are like the most frequently queried data for log analytics use case, are saved in a separate set of segment than the success log, thus improving the overall search query performance. Now we can probably look into like the core benefits that we are observing with context-aware segment. Actually, at a high level, we observe two major core benefits with context-aware segment. First is data isolation, and second is the query optimization. So, with context-aware segment, we are ensuring that group-specific data we are ensuring data isolation by storing each group document in a dedicated segment. So, group belonging to separate documents belonging to separate group now will be saved in their own dedicated segment, allowing some form of clear separation between them. Second improvement that we are actually observing with context-aware segment is query optimization. So, right now, since we are storing relevant document we are storing each group documents within their dedicated segment. For during the query time, we can narrow down the search space by querying only the relevant document, only the relevant segments. So this essentially improves the overall query performance as well. Besides the two major benefit that we receive with context-aware segment, there are few additional performance gain that we will observe with context-aware segment. First part is inherent data ordering. Now, like actually, an additional part of context-aware segment is that it is on some level doing a form of bucket sort, which brings some level of ordering for the documents that are saved within a particular shard. Now, this essentially improves the overall performance of OpenSearch, since certain data structure like Lucene, certain data structure like BKD, which is a Lucene construct, tends to perform better when there is certain order, when the data is ordered. Second additional improvement that we see with context-aware segment is improved compression, which again comes from the fact that we are bringing certain level of ordering to the data. The third improvement that we see with context-aware segment is we can even use context-aware segment to control cardinality of the document within a particular segment. So, since we can, with context-aware segment, we can actually define the group in a way that the diversity of the document within a particular segment is controlled. This tends to benefit certain data structure like star tree, where as the cardinality of the document is increasing, the performance of star tree actually as the performance of the star tree degrades. So yeah, like these are like some few set of improvement that we actually observe with grouping related documents into same segments. Now, since we have defined like what context-aware segments are, and like basically what are the key benefits that we are getting from context-aware segment, let's probably give some idea around how user can define this group in general. So currently, for OpenSearch, each workload is different, and user may want to group data in different ways. So it is important for OpenSearch to have a way for user to be able to configure these groups. To do this, like user can specify a grouping criteria which helps OpenSearch understand how to group documents within a particular segment. So in order to do this, OpenSearch will provide a configuration inside index mapping where user can specify a grouping criteria definition. The grouping criteria definition in general will consist of like two parts. One is the field on which the user wants to group the data on, and second part is actually the logic which will be, or a particular script which will be executed on each document to figure the group corresponding to for this particular document. Let's probably try understanding this via an example. So suppose for a log analytics use case, customer have logs for 2xx, 200, 404 and 500. Now these are the status code of the logs actually. These are three different status code logs which customer is having for their workload. Now by defining the grouping criteria on the status code, as we can see in the example here, customer will be able to logically group the documents, logically group the logs into three buckets, where like the first bucket will contain all the success logs, second buckets 4xx, and third bucket all the error logs. So basically, in case now if customer wants to query a 5xx error during a certain time period, it only needs to scan the segment which contains 5xx error logs. So this essentially improves the overall query performance. Now, like basically, since we have defined what segment grouping is, as well as what how user will be able to how user will be able to define the groups within a particular segment, let's probably look into we can start looking into how we can support context-aware segment within the OpenSearch. But before looking into that, let's probably talk slightly about what is the current data layout within the OpenSearch. So currently, as mentioned by my colleague, like OpenSearch has an index. Within that index, the data is distributed within shards, and within shards, the data is actually indexed inside segments. So, basically, the distribution of documents that happen within segment is essentially controlled by two key operations. It's either indexing or segment merges. And currently, during for doing an indexing, OpenSearch currently uses a Lucene construct called index writer to index document within a particular segment. Now the issue with this is that for a particular shard right now, OpenSearch uses a single index writer to index document all kinds of document within a particular shard. Issue with this is that since connected with the previous example, like issue with this is that since both 4xx, 5xx and 200 logs will be indexed using the same index writer, the underlying segments that will get generated, it will contain a heterogeneous mix of documents actually. So another thing to point here out is that basically the data distribution, the scattering of data happening during segment merges. So currently, as we already know, like OpenSearch currently periodically combines smaller segment into larger segments using a process called segment merging, and this is done to like keep the file handles in check. And basically OpenSearch is using a Lucene construct called merge policy to determine when and how segments in an index are merged. Now both the existing merge policy, which is like tiered and log analytics merge policy, which currently exist for Lucene and OpenSearch, both of them tries to optimize either for the write speed or the insertion order, and it doesn't take into consideration the anticipated query pattern while merging the segment. This again basically leads to further scattering of the related document that could have been grouped together across the segments. Now, like since we looked into the current issue or current data layout within the segment and how it is causing the data to scatter across related data to scatter across different segments, we can start looking into how to solve this particular issue and how we achieve data isolation in OpenSearch. So first, like the first flow which we target is like during indexing. So currently, as discussed, OpenSearch is using a single index writer to index document to a particular shard, and which was initially causing some form of heterogeneous mix of documents within the segment. So instead of doing that, to allow like related data are saved within the same segment, what we do is we now maintain a single index writer per group per shard actually. So what will happen during indexing is that whenever a indexing request to index a particular document comes on a particular shard, OpenSearch will first evaluate the group corresponding to this particular document using the grouping criteria function that we discussed earlier. Now, like once we have evaluated the grouping criteria function, it will redirect that particular document. Once it has evaluated the group corresponding to a particular document, it will redirect that document to the corresponding group specific index writer. So by doing this, it will ensure that all the document belonging to a particular shard, all the document belonging to a particular group are indexed using separate index writer within a particular shard, thus avoiding any form of cross-contamination. This is during indexing. The second part, the second workflow where we try to maintain data isolation is segment merge. So basically, in order to do this, we plan to introduce a new merge policy within OpenSearch called context-aware merge policy, which basically will merge the segments, which will merge only those segments together which belongs to the same group. So giving for the example, connecting with the example for the log analytics, suppose say there are few segments belonging to 200 and some segments belonging to 400. This new merge policy will consider whether a merge or whether a new merge can be triggered only for the namespaces of segments which belongs to status code 200 or which belongs to status code 400, and the new merges that will get triggered will be specifically for that particular group, and it will be an independent of each other. So by doing this, we basically ensure that this group invariant that we are introducing during indexing is maintained even during the segment merges. Now, now we have since elaborated how we plan to support context-aware segment within OpenSearch. Let's probably break down on how we achieve data isolation across both indexing and merge. During indexing, a major part that we need to note down here is that for indexing document belonging to different groups inside a shard, we are using separate index writer. So since the writers are separate, different group data will never share write path or buffer space during their entire indexing flow. Second part on how we achieve data isolation for context-aware segment is context-aware routing. So basically, during indexing, for each document, we also identified that before even indexing a particular document, we identified the group for which this particular document belongs to. So and post that we redirected the ingestion request for this particular document to its respective index writer. So by doing this, we are guaranteeing data isolation for document across groups. Since this is because for each for indexing document for each group, now we are using a separate index writer. So this essentially avoids any form of data mixing in between documents belonging to two different groups. The third part, or the second flow, like where we try to maintain isolation, was at the merge path in the merge flow. So we basically for doing the segment merge, we basically are introducing a new merge policy which only merges segments that belongs to the same group, and it maintains by doing this, it maintains grouping invariant even during the segment merges. So by doing this, we are using the new merge policy, we are able to ensure data isolation even during the segment merges. I think with this, I will conclude the indexing flow, and I would like to hand over the slides to Tejas, who will cover the search flow.
Thanks, Rishav, for covering the indexing flow. So the entire grouping of data within indexing was to prevent search bottlenecks. Now, in general, when OpenSearch tries to execute search, it just goes over all the segments and iterates through each and every segments and executes search on it. Now, because we have grouping of data, we can easily prune the search spaces based on the queries. So the goal here with context-aware segment would be to just narrow down the search space as much as possible. So yeah, that way, that's where the benefits of performance lies, where we are able to narrow down the search space. Now, just to see how we achieve that, we in the current workflow, we added two new steps. Like apart from query processing and executing the search, there are two additional steps that are added to leverage the grouping of segments that we have done during indexing. One is the criteria extraction. To be able to identify segments that we want to execute search on and leverage that grouping, we need to know the query, and then we need to evaluate the query and figure out what is the grouping criteria for, that enables us to prune the search. So this basically goes through and evaluates the entire query to figure out whether we are able to find any group in it. And the second step is crucial for performance benefits, which is basically segment selection. Out of the entire search space, we want to only execute search on segments which belong to that group that we executed, that we found out from the query. This is a very high level flow. I have like a barcode link there just in case you are interested in the details of what the flow looks like. Just to go a little bit into detail of what these two steps are. The first one is basically trying to figure out a grouping criteria based on the query that is being executed. Now, to start off with, we were focusing on the Boolean clauses with term and range queries, where we are using priority-based extraction logic, wherein as soon as the query comes to OpenSearch, it tries to figure out whether there's a filter clause. In that filter clause, if we find a grouping clause, we just short circuit must and should clauses. If we don't find it, we again go to must clause and then do the same thing and then fall back to a should clause. If should clause doesn't, if no grouping criteria is found in the should clause, then the query is going to be executed on all segments. So we don't get any performance benefits with the grouping. So it's important that the query is formed correctly. Just to give an example of the status code, I have a sample query on the slide. Here we are just trying to find the status code of 400 and then a throwable inside like a term, trying to match that category. So this will try and extract status code. The extraction logic will try and extract status code, and we saw a script that was there in the grouping criteria mapping example that will execute that script with the 400 value and then finally get 4 as the group. Now the next step was to have segment selection. Now a naive way to do segment selection would be like segments already have a metadata of what group they belong to. So just go through iterate through the entire segment and filter out only those where we can execute search on based on the criteria that was extracted. But we wanted to make sure that there is no additional runtime cost in doing so. So if there are too many segments and too much data, the iteration of the entire thing will definitely add to latencies. To get around that, what we are leveraging is a refresh cycle. Once data is ingested, to make it available for search, there's something called as refresh operation, which basically makes data available. That is where the flush indexing is executed and index is built basically. So during the refresh cycle, since we have all the segments during the refresh cycle, we go through the segments during the refresh cycle and then extract all the grouping and create an in-memory map of the group as well as the list of segments. And these are just references, so it doesn't add up the memory. Now, once we have this mapping of criteria to all the segment list, it's just an O of 1 operation during query execution to just identify what segments need to be used to execute search. So yeah, pruning the search space as well as making sure that there is a mapping already present during query execution gives us all the performance benefits that we see with context-aware segments. I would like to talk a little bit more about the future. Right now, we have a mapping which the user have to provide to make sure that the data is grouped correctly. In future in the roadmap, what we are planning is for at least for certain use cases, like very common use cases like log analytics, we can just do the mapping out of the box, like create groups out of the box, and user doesn't have to have that mapping. And the other part is the storage tiering, where certain users want, if the data is too large, they want warm tier as well as hot tier just to save costs, and that support will also be there in the future. So yeah, with this, I would like to open it up for questions if anyone has it. Yeah. Thanks. Go ahead.
Yeah, so my understanding is segments are immutable, right? So once they're created, they cannot be updated. So I'm not anticipating all the groups or documents are going to come at the same time, meaning that you're going to keep having to create new segments even if the group exists in an existing segment because you can't update it, right?
Yeah.
Would this cause way more segments to be created?
Yeah, I think that's actually a valid point. I think, and this is an issue that we observed with context-aware segment as well. That since even in the merges, even during merges evaluation, earlier we used to evaluate which all segment needs to be merged on the entire set of segments and on the entire documents. Now, since we are reducing the scope on which we will be evaluating the merge policy on to the respective group, the number of segment is something which is increasing, and I think this sometimes causes even the file handles to grow as well. So in order to avoid that, what we did was that we basically tuned the merge configuration in a way that an aggressive merging happens for the segments that belong to a particular group. Some of these configurations are basically changing the number of tiers, or basically setting the maximum number of segments that can be present inside a particular tenant. So once that limit started breaching, we basically it will start doing an aggressive merges, and it will keep the number of segments in control. Sorry.
Yep.
Does that mean that when you flush in the segments, there will be one big chunk of 200 and just one document of 404? Does that happen if that's the case then? Are you counting them essentially on your merges to take care of that problem?
Yeah, basically it may be possible that say there was only one document for which a separate segment got created. But yeah, eventually the merges will take care of restricting the number of segments that will belong to a particular group. I think this issue even happens right now as well, right? Say only one document got indexed, when flush will happen, for that a single segment can get created. But yeah, I got your point. I think with context-aware segment, this will eventually start happening on individual groups. So the number of merges will basically eventually will take care of. Yeah, I think that's a very valid point. I think we, in order to ensure that cardinality of the document, cardinality of the groups, or the number of groups is not exploding, we plan to add certain guardrails actually, so that in case the cardinality or the number of groups is increasing beyond that particular limit, we will start failing any further indexing request. Or there is another way, basically I think this is a user configurable setting, that either fail the request in case the cardinality is breaching that particular certain limit, or basically use a default group for all the new indexing, all the new document, or all the new document with new groups actually.
Like others group?
Yeah, some sort of others group actually.
So in your indexing slide, you said something around, you have a step where you evaluate all documents to determine how many groups are needed. How are you able to do that before because you don't have all the documents coming in at the same time? There might be newer documents that have newer groups in the future, and so would that mean that you create on the fly new writers?
Yes. Yes. As in case the limit is below that particular configured threshold, if a new document comes in where basically for which like there is no existing index writer in the index writer map, we will create a new index writer for this and use that index writer to index the document.
So then the implication here is that potentially indexing can be a lot more CPU intensive if you're doing this because there's way more writers that could be taking up CPUs versus one writer.
Yeah, I think like we did like validated this. I think we did run some sort of benchmark here to see like how many maximum number of writers that a particular node can support across like different node types. And basically like for I think for R6G 2x large, I think we were able to support like say about 30k tenants on a single node actually. This is one thing. And second part is like basically index writer in essence it is actually almost is having the same weight as a DWPT. So like currently if you are aware, like basically when we say a particular segment like in Lucene term, that is actually getting mapped to a particular DWPT actually. So DWPT is basically a document writer per thread. So basically when we are in essence like basically when we are indexing a particular document to an index writer or when we are indexing a document to a DWPT within a particular index writer, those two are having almost the same weight actually. So like in the current scenario, what happens is that basically like there is a single index writer and within that like basically there are different DWPTs which takes care of handling the request from the index writer. So when we try indexing a document to a particular shard that falls onto the index writer will like move it to a particular DWPT, and in case any DWPT is not available, it will create a new DWPT similar to what we are doing here for the group actually. So
yeah, so like just to answer the question, I would say like we saw a little bit of an increase in CPU, but we are controlling it with refresh intervals. So because as soon as the refresh interval is done, as soon as the flush happens, we just throw off the entire index writer. So any new documents that are coming in will need to grab a new index writer at that point. So that's how like the number of index writers is also controlled. So if say refresh interval goes from 1 second to 60 seconds, yeah, there'll be a shoot up in the entire CPU. But like as long as there are default refresh intervals like that, it doesn't go beyond certain point, like we have seen around 800 index writers at a time in a particular node. So the CPU utilization doesn't spike up like eight times or something like that. It's just a little bit more. Yeah. Okay. Then, thanks. Thanks everyone.